This video will discuss reflection of light and images formed with a plane mirror. If a stone is dropped into a pond, circular waves emanate from the point where it landed. Rays perpendicular to the wavefronts give the direction in which the waves propagate. As one moves further from the point, the wavefronts become more nearly flat. The law of reflection states that the angle of incidence equals the angle of reflection. In this diagram, you see a perpendicular line drawn to the mirror called the normal. The incident wave is illustrated by a purple arrow that is hitting the mirror where the normal intersects it. The angle between the incident wave and the normal is called theta I, or the angle of incidence. According to the law of reflection, when that wave bounces up, if you measure the angle between the normal and the reflected wave, theta R, the angle of reflection, will always be equal to the angle of incidence. However, reflection can be specular or it can be diffuse. So if you think about a nice smooth mirror, when all the rays bounce off the surface, they bounce off with reflected rays that are parallel to each other. So you see a perfect image. But look at your desktop. You can almost see a reflection, but it's very, very diffuse. Diffuse reflection occurs when the surface is not smooth and reflected angles bounce off according to the law of reflection, but the reflected rays are not parallel to each other. So you don't get a perfect image. If we wanted to think about how a plane mirror makes an image, consider the flower. You can draw and construct the rays from the top of the flower that go from the top of the flower to the mirror and bounce to your eyes. Notice that these two reflected rays will never intersect each other on the side of the mirror that your eye is. But if you project them back, they do intersect each other. Same thing with the bottom of the base. If I take two rays that come from the base and I look at their reflected rays as I would see them, those two reflected rays never ever intersect. But if I dot them behind the mirror, they intersect at the bottom. The result is that the projection of the reflected rays behind the mirror form an image, the image that we see. When we look in the mirror at the flower, if the flower is 1 meter in front of the mirror, then the image looks like it's 1 meter behind it. Also, the image is flip-flopped. The left is in the opposite direction of the right. But if I put a piece of paper right here where that image is forming, I won't see the image on the paper because there's no real light rays intersecting, just projections of light rays. So this type of image is not a real image. A real image can be projected onto a screen because it forms where real light rays intersect. However, it is an image and we can see it, but there's not really anything 1 meter behind the mirror. If I put a piece of paper there, I don't see the projection. Plane mirrors always produce an upright image, but it's reversed right to left. A mirror image appears to be the same distance behind the mirror that the object is in front of it. And the mirror image is the same size as the object. But the other thing that we need to realize is that the image cannot be projected because it's forming on the side of the mirror that has no real light rays. So you can't put the paper where light rays are intersecting and see this image on it. That's called a virtual image. Virtual images in a mirror always form behind the mirror where there's no light rays, and they're always upright images. A corner reflector reflects light parallel to the incident ray, no matter the incident of the angle. So you get to see the image from all sides.